Okay, here's a quick little video on the subject of atomic units. Atomic units are widely used in quantum mechanics and in particular in quantum chemical calculations such as the output of, say, Gaussian or games or any of the other uh, well-known quantum chemistry packages. They are the sort of typical units that those packages use. Often there's some capability to convert those units to more familiar uh, joules and kilojoules per mole and things like that. However, kind of the native units of these packages are these atomic units. Uh, in addition, another reason to learn about atomic units is that they provide us a way to make our quantum mechanical equations a bit simpler, easier to follow, with less sort of cabbage, fewer constants hanging around, so that it's a little bit clearer what the principal variables are that are in our equations, and it tends to make things a little bit neater and easier to follow. So for an example, let's take a look at the Hamiltonian for helium. Okay, helium has two electrons and one nucleus with a charge of 2. And if we look at this Hamiltonian here, we've got the sort of kinetic energy term here, right? That includes your minus h bar squared over 2 times the mass of an electron, and the del 1 squared, that has to do with the kinetic energy of the first electron, let's say, temporarily assigning them labels, right? We know we have to be careful about that, but we know we have these labels. And del squared 2, which is the kinetic energy of the second electron. Then after that, we have, of course, the Coulomb interaction between the nucleus and the first electron. That's going to be E squared Z over 4 pi epsilon naught R1, with a minus sign, of course, since it's attractive Coulomb interaction between different charges. Positive charge on the nucleus, the negative charge on the electron. And then, of course, there's a similar term, but for the second electron, this Coulomb term, that has to do with the interaction of the second electron with the nucleus, and it has E squared, where E is the charge of an electron, times Z, the sort of atomic number of the nucleus, divided by 4 pi epsilon naught R2. And for completeness, I should also mention that epsilon naught is the dielectric permittivity of free space. Then we finally have this electron-electron repulsion term, E squared over 4 pi epsilon naught R12, where R12 is the distance between the two electrons at any one moment in time. Of course, the electrons are spread out, and so evaluating this Hamiltonian is difficult, and that was the subject of a previous lecture. So we can imagine simplifying this Hamiltonian a bit if we just replaced a lot of these constants with 1, right? If we set that the mass of an electron and the charge of an electron, and so mass of an electron, charge of an electron, h bar, 4 pi epsilon naught, we set all of those constants or collections of constants equal to 1, then we could really clean up our wave function. We'd end up with something that looks like this. H equals 1/2 parentheses del 1 squared plus del 2 squared, and parentheses minus z over r1 minus z over r2 plus 1 over r12. Seems great, right? A lot cleaner. But you might say, well, you can't just set constants equal to 1. Sure you can. Essentially what you end up doing is redefining the length scales and the energy scales and the time scales of this system. And so this essentially defines a new set of units that we call the atomic units. And one of these units we've seen already is the Bohr radius. So the unit of length, the natural unit of length in these atomic units is the Bohr radius, and it's given by, of course, A0. And we can convert between this atomic unit of length, the Bohr, right? And those terms can be used interchangeably. You can say atomic unit of length, or you can say Bohr, like the electron is at 1 Bohr from the nucleus or something like that. Or you can say it's at 1 atomic unit of length from the nucleus, something like that. Anyway, so you can use those terms interchangeably. And then, of course, to convert to conventional units, we know that the Bohr radius is 52.9 picometers or 0.529 angstroms. Similarly, we get a new unit of energy, the Hartree, and this is a unit that you have probably already run across in the laboratory portion of this course. And the Hartree is essentially the same as 2 Rydbergs. That's another constant that we've run across before. And in terms of joules, it's 4.360 times 10 to the minus 18 joules. So what happens when we replace our regular units with these atomic units? Not only does it simplify the Hamiltonian as we showed above, but then also your wave functions end up looking simpler. Like for instance, in conventional units, the hydrogen 1s wave function looks like this, where R10, that's the radial portion of the hydrogen 1s wave function, is 1 over square root of pi, and then we have this z over a aught to the 3/2 power, and then we have this exponential part, e to the minus z r over a aught. When we convert to atomic units, this becomes z to the 3/2 over square root of pi, right? We've essentially gotten rid of the a aught equals 1, and our exponential part is e to the minus z r. Right, so it drastically cleans up that. Similarly, in our energy levels of the hydrogen atom, for the energy levels part, the expression for energy levels of a hydrogen atom would be minus 1 over 2 n squared, where, of course, n is our quantum number. And that pretty much does it. So we have these atomic units. They allow us to rewrite our Hamiltonian in a more compact form, where the important variables like length and the coordinate and the coordinates and the labels like R1 and R2 are more clear, right? They really pop out. They're not sort of hidden behind this sort of wall of constants. And it also gives us a simple way to represent the wave functions as well as the energy levels. And of course, as a final point, the energies given in the games package for the PChem lab are typically given in these kind of atomic units. The other thing I would say about this in closing is that we're going to, of course, switch back and forth between the atomic units and sort of the conventional picture as we see fit throughout the rest of the course. And that's all I have to say about atomic units.